here is our practice question solved for our lessons that you see online for quantum physics. And I have here the formulas that you will see on AP exam on the top right. So these are the only formulas that are given on AP exam. So let's look at the question. A sodium surface is illuminated with light of wavelength is given. So the wavelength of the light is given. It is 0.3 micro. Micro means 10 to the negative 6 meters. The work function for sodium. So the work function, sometimes they use W. I like this one for the work function, phi. So that is 246 electron volt. So calculate the energy of each photon in electron volts, the maximum kinetic energy of the ejected photon electrons, and the cutoff wavelengths for sodium. And we know that the Planck's constant is equal to 14 10 to the negative 15 electron volts. So if we use it in with electron volts, we keep Planck's constant as well as in electron volts. And so if I want to find the energy of each photon, I have energy of the photon, which is the Planck's constant, times the frequency of it. They don't give you the frequency, but they give you the wavelength. And so it's the Planck's constant, and then I have, instead of the frequency, the speed of light over the wavelength. So that is 414 10 to the negative 15, and this is 310 to the 8, and the wavelength is 0.3 micro 10 to the negative 6. And what I get is 414 electron volts. For B part, they ask to find the maximum kinetic energy of the ejected photoelectrons. So this was for A. I'm going to do B in different colors. So this is my B. So you know that the energy of the photon is equal to the work function plus the kinetic energy of the electrons after they are ejected. So you have the work energy is 414. The work function is 246 electron volts, and what's left is the kinetic energy of the electrons. So the kinetic energy of the electrons is equal to 168 electron volts. And then for C part, find the cutoff wavelength for the sodium. So I know that the work function is equal to Planck's constant and the threshold frequency, the minimum frequency needed to cut off the electron from the surface. So I could rewrite it as Planck's constant, and then I have C over lambda. Then lambda is equal to the wavelength that I'm looking for, or the wavelength that they ask me for, threshold cutoff wavelength, and that is equal to hc divided by the work function. And if I plug in my numbers, looks like it's going to be 505 nanometers, nano 10 to the negative 9. In question 5, they ask that the medical X-ray machines typically operate at the potential difference of 1/10 to the 5th volt. Calculate the minimum wavelength their X-ray tubes produce when electrons are accelerated through this potential difference. So if you know the definition of the voltage is the work done on the charge, and work is the change of the potential or kinetic energy over the charge. So I can rewrite my formula as voltage is equal to, in our case, it's the work the energy that the electron has. So that is the Planck's constant and the frequency divided by the charge. And here I have the Planck's constant. Instead of the frequency, I can say it's the speed over the wavelength, and I still have the charge. So the wavelength is equal to the Planck's constant, speed of light, Q and V. So if I plug in my numbers, I have 663 if I calculate joules, 10 to the negative 34, and that is times 3 10 to the 8, 10 to the 8, and divided by the charge of the electron, 1.6, 10 to the negative 19, and the voltage they give you 10 to the 5th. And looks like the wavelength is equal to 1243, 10 to the negative 12 meters, or 1243 picometers. Pico means 10 to the negative 12. For number 6, they say, what the potential difference would be necessary to produce gamma rays with a wavelength of 10 to the negative 15 meters. This wavelength is about the same size as the diameter of the proton. And again, it's a potential difference, so I can apply again the voltage formula. So it's the work or the energy needed to move the charge. So I can do the same. They ask me potential difference, so I need to find V. The work is the Planck's constant, and they give you the wavelength. So instead of writing the frequency again, I'm gonna write C over the wavelength, and then I have the charge of the electron. If I plug in my numbers, so I have the Planck's constant 663, 10 to the negative 34, then I have speed of light 310 to the 8, and then I have the charge of the electron 1.610 to the negative 19, and then I have the wavelength that they gave me, let's do just 10 to the negative 15. So V is equal to 1243 10 to the 10th volts. Or actually 10 to the 8th volt, right? 10 to the 8th volt. For number 7, they say estimate how many visible light photons 100-watt light bulb with a wavelength of 500 nanometers emits per second. The bulb has a typical electric efficiency of 3%. 97% of the energy goes into heat, and they give you that how much watts goes into heat. So when they say it's a 100-watt bulb, so that means emits per second, right? So I have the power is equal to work per time, and here I have 100 joules per 1 second gives me 100 watts. So that means the work that can be produced by the bulb is 100 joules per second. So that is the work or energy. So I can write here energy. But only 3%, as they say, only 3% is going to be the energy emitted as light. So that means only 3 joules per second is light. 97% of energy is, or 97 joules per second is heat. So that means that my actual work energy that is emitted photons, that is only 3 joules. So I'm only going to use this energy because the rest is just waste for the heat. And I also know that the energy of 1 photon is, let's do this way. Instead of writing pH for photon, I'm going to say of all photons emitted, right? This is all photons. There's number n of the photons. but one photon is Planck's constant and the frequency. They don't give me the frequency, but they give me the wave. So that is 663 10 to the negative 34th. And instead of the wavelength, instead of the frequency, I have the speed of light, 3 10 to the 8. In the wavelength, they give you 500 nano 10 to the negative 9 meters. So that energy is going to be equal to, I have 0.04 10 to the negative 17 joules. So this is energy of one photon, and I have 3 joules of energy. So to find the number of how many photons are in 3 joules of energy, so 3 joules of energy live in the bulb, and this is the energy of one photon. So to find n, I have to divide 3 joules by 0.04 10 to the negative 17. And my answer is going to be 75 10 to the 17 photons. So that would be my answer for number 7. For number 8, they say find the de Broglie's wavelength of a proton. The mass of the proton is given, and this proton is moving at the speed of 1.110 to the 7 meters per second. So for de Broglie's wavelength, I'm going to derive this formula how they usually explain this. So the energy is equal to mc squared, and here they break it into mc and c. So mc is the momentum p times c and equals to, and energy is also equal to of the photons, the Planck's constant and the frequency, and that is the same as hc over lambda. So I can rewrite this part is equal to this part. So I have pc is equal to hc over lambda, and c cancels. So if I solve for the wavelength, then I have h over p. And this is true for the photon, but because particles can be represented as waves as well, so I can rewrite it as hmv. So instead of p, I have the momentum. And so I'm going to use this formula to find the de Broglie's wavelength. So if I plug in my numbers here, I have 663 10 to the negative 34 divided by the mass of the proton, which is 167 10 to the negative 27, and the speed is 10 to the 7. So that gives me the wavelength equals to 39.7 femtometers. Femto means 10 to the negative 15. So for number 9, they say the work function phi of aluminum is 4.08 electron volts. What's the threshold frequency required to produce photoelectrons from aluminum? So I know that the work function is equal to the Planck's constant, the threshold frequency or the cutoff frequency. So if I'm looking for the cutoff frequency, that is going to be 4.08, and my numbers are given in electron volts. So I have to plug in my Planck's constant in electron volts. So that is 14 10 to the negative 15, and that will give me almost 1 10 to the 15 hertz. So that's for A. For B part, classify the electromagnetic radiation that can produce photoelectrons of this frequency, and you have to look at the chart. And the chart, so the electromagnetic chart. Here I got the chart for you. So if you see that the electromagnetic spectrum is classified by the wavelength and by the frequency. So this part is going to be the frequency, And if I look at 10 to the 15th, so here is 10 to the 15th, and that's ultraviolet. So my answer is ultraviolet. So I got these two answers so far. For C, if light frequency 410 to the 15 hertz is used to illuminate the piece of aluminum, what is the kinetic energy or maximum kinetic energy of ejected photoelectrons? So we know that the energy of the photon is equal to h times the frequency of the photon, and we just found the frequency of the incoming photons. And they say that, the frequency of the photon is given 410 to the 15, right? So this is the cut-off frequency. But the ones that they give you is here, so in C. So I have everything is in electron volts, so I'm going to keep electron volts. So 4.1410 to the 15th, and times by 4, 10 to the 15 hertz, negative 15 for Planck's constant, and that is equal to, so that's the energy of the photons that are incoming, and that energy is going to be spread between two things. One is the cut-off energy, cut-off work energy, which is 408, yes, the work function is 408 electron volts, plus the kinetic energy that is left. So from here I see that the kinetic energy is equal to, and if I do my calculations, it should give me 12.5 electron volts. For the second part, they say what is the maximum speed of the photoelectrons, and mass of the electron is given. So if this is the kinetic energy, then I have 1/2 m of the electron v squared. And if I plug in the mass of the electron, and I already know what the energy of those electrons is, I can find the speed. So the speed will be equal to 2.1 10 to the 6 meters per second. If the light described in point B, so point B, were increased by a factor of 2 in intensity, what would happen to the value of kinetic energy? So because intensity is increased, that means you have the metal, aluminum, and photons are coming here. Each photon has the photon energy E, and when they pulled out, so there is going to be like I'm going to do 3 photons, 3 electrons. They all have kinetic energy, the one that we found, the kinetic energy. But now the intensity increased. That means there is more photons of this energy, of this given energy is coming. So that means there will be more electrons of this kinetic energy flying away from the surface. So even though there would be more electrons coming, so if there before 3 photons, now I have 3 more photons, so I have 3 more electrons flying out, but their kinetic energy is still going to be the same. So the answer is going to be the same photons with the same kinetic energy, because intensity means there's more photons. You have to, let's look right here in different color. So if you increase the energy of the photons, then this is the energy needed, or the work function that is needed to pull out each electron. Then you would increase the kinetic energy. So you have to increase the not intensity, but the energy of the photons in order to increase the kinetic energy. Intensity just gives you more electron at the same kinetic energy. So for number 10, we have the first 5 energy levels of an atom are shown. If the atom begins in the N3 level, what photon energies could be emitted as it returns to its ground state. So if it begins with the level 3, so here's the level 3, they ask you what photon energies could be emitted to get to the ground state. So you could go from level 3 to the second and then to the ground, or you could go straight to the ground. So the energies that could be emitted is the difference between the states. So for the purple one, I have 15 electron volts and 7 electron volts. So negative 15 minus negative 7 gives you negative 8 electron volts. So that's how much energy you could emit. Or the red one and the longer purple one, exactly the same. So you would just have one of these ones, so it doesn't matter you go straight down or, so I'm just going to write the red one. And the other one would be 62 minus negative 7. So that gives you negative 55 electron volts. You could also go, if you got to the level 2, you could also go to from 2 to 1. So it's either straight down, I could erase this one. It's either straight down, let's do this way. You could go this way and then down. So I have negative 8, and then from 62 minus negative 15 will give me 47. So that is negative 47 electron volts. And then the red one straight down. So that would give me 55 electron volts. And the next question is, what could happen if this atom, while in undetermined ground, or undetermined or ground level energy state, were bombarded with a photon energy of 10 electron volts? So if you have 10 electron volts are coming, so what would happen? So let me erase this part right here. So here is the wavelength of, or the photon of 10 electron volts coming. So in order to go from 62 to 15, you would need 47 electron volts. If in order to go from 62 to 7, you will need 55 electron volts. In order to go from 62 to 4 electron volts and so on, none of them have enough energy. 10 does not have enough energy to kick out the electrons, so nothing would happen. For number 11, we have how much energy must the ground state electron in a hydrogen atom observe to be excited to the N4 level, and the ground state energy of the hydrogen atom is negative 13.6 electron volts. When the electron is, let's do that A first. So how much energy must the ground state electron in the hydrogen atom to be observed to go to the 4th level? So the formula for the hydrogen atom is energy is equal to 13.6 electron volts divided by n squared. So I have 13.6 divided by n squared, which is 4. So squared, that will give me energy on the 4th level, 0.85 electron volts. So if the ground level is 13.6 and the 4th level is 0.85, so how much energy must the ground state electron of hydrogen absorb? So you would have to absorb this much energy. So that is 13.6 minus 0.85, which gives me 12.75 electron volts. So this is how much energy you have to absorb to jump to the 4th level. Now, if the electron is already on the 4th level, what wavelengths are possible for the photon to emit when it goes back to the ground level? So you could go this way, you could go this way, and you can go this way. Or you could go from the 4th to this one and then down. or which I can avoid calculating because I already have the gray one, which is that one. Or you could go straight down. So if you go straight down, we just calculated that number. That is energy is equal to 1275. And if it loses 1275 energy in electron volts, then I can do h times the wavelength, right? So I need c over lambda, and I'm gonna plug in my electron volts, the Planck's constant, 414, 10 to the negative 15, then I have 310 to the 8, and then I have the wavelength. So the wavelength is equal to 97.5 nanometers, 97.5 nanometers. So that would happen if it jumped right from the fourth level to the ground level right away. Then for the green one, what if it goes from the fourth one to the second one? So if it goes from the fourth one to the second one, I have to subtract, I need to calculate the energy on the second level. So the energy on the second level is going to be, I'm going to use the same formula. So the energy on the second level is 13.6 divided by 2 squared. So that will give me 3.4 electron volts. And the difference between 0.85 and 3.4, so 3.4 minus 0.85, that's how much energy it has to lose to go from the fourth level to the second level. And that is equal again hc over the wavelength. So if I plug in my electron volts, Planck's constant, and calculate the wavelength for the green light, the one that goes from fourth to the second, it's not the green light, but for the green air, I get 487.5 nanometers. And then for the last one, for this one, I will have the difference between 13.6 and 3.4. So to go from the second to the first, that will give me 10.2. And again, it's the Planck's constant c over lambda. And in this case, I get lambda is equal to 122 almost nanometers. And then I think I skipped one more that is going from, let me erase a little bit here. I am limited to only 30 minutes of video, so I'm going to do it quickly. So I skipped the one going from the fourth level to the third level. So to go from the fourth to the third, I have to find the energy on the third level. So that is 13.6 divided by 3 squared, and gives me 151 electron volts. So when it jumps from the fourth one to the third one, it will lose, or it will emit 0.66, so it's 0.66 electron volts, and that is again equals to h times, I'm doing the gray one, I guess, divided by, it have the c over lambda, and that gives me the wavelength of 1883.5 nanometers. So these are the possible wavelengths, and I have about 30 seconds before the video runs out of. So I hope this was helpful.